Okay, we're going to go ahead and get started. Welcome everybody to this week's Community Zoom. I just realizing this is an older picture, but it's starting to look like this here in the Green Bank area. The leaves are turning, and fall is a wonderful time in the Green Bank Mountains here. Um, so we're whoops. We finished the painting. We painted the upper part of the phenom, not we, I mean our contractors did, and there's some pictures here showing them hanging from the beams, and you can see you know, the difference it made, like especially this one over on the left here. So they sandblasted down to metal, they put the primer on and painted. So we did the upper part of the feed arm basically this summer. That's all completed. What's going on now is we're replacing 5 wheels. If people remember, a couple years ago, we had one of the wheels fail, and then we inspected them and noticed that we had some issues. So we're in the process of replacing wheels, and that work's ongoing this week. And we expect to be back up and observing on the 26th of September. So those who have projects in the queue, get your scripts ready and enabled for the end of September, early October. And as a reminder, we have GBT training workshop in November. You can go on the web pages, and if you have yourself or your students or postdocs, have them basically put in their application or register. It is going to be virtual. We're going to do that all virtual, and we have a good program there. So if you need somebody that you know that is a GBT user and wants to learn how to use a GBT, please have them register. So we're going to go ahead and get going here with our talk. John, you can go ahead and start loading up your slides. Our speaker today is John Cannon. He's from McAllister College, and he's going to be talking about H1 with the GBT and nearby dwarf galaxies. So I'd like to remind our participants, if you have questions, please use the Q&A box down at the bottom of your Zoom window, and we will have a Q&A session at the end of the presentation. Okay, it looks good, John. You can take it away. Thank you.
Great. Thanks very much, Dave, for the nice introduction, and thanks to each of you for being here today. It's my great pleasure to be able to talk to you about an ongoing optical and radio campaign to populate the local census of dwarf irregular galaxies. This work is one of the showpiece components of the PhD thesis of Alexandra Nazarova, who should be here on the call, I believe. And so an image of Alexandra at the GBT from the Single Dish Summer School last year is shown at left. And this work has also involved many other individuals who have done some heavy lifting, including Maxim Chazov, another third-year graduate student at SAO, Dmitry Makarov, and Yuri Karachentsev, and then a couple of McAllister students that I'll mention later on in the talk. To give you a sense of where we're going to go together today, I'm going to talk about first the physical properties and the cosmological importance of low-mass galaxies. We'll then talk about previous efforts to populate the local census of these galaxies, and then talk about the new work that our team is doing, specifically a manual examination of the DESI Legacy Survey images to identify candidate local volume systems. We then follow those up with a gorgeous GBT dataset, and we're now in the first steps of VLA follow-up of some of the most intriguing sources from that effort. So first, let's think about the physical properties of these galaxies. To get a sense of where we're going to go together, let's think about a massive disk-like star-forming galaxy. So here's an image of Andromeda. And these systems are titanically massive compared to the ones that we're going to be talking about today. And I list at the bottom here a couple of salient parameters, not meant to be exact values, but representative parameter values of stellar mass, mass and H1 ratio, and physical sizes. And so these big star-forming galaxies, of course, have absolute magnitudes less negative than, say, negative 21. And these are the very luminous objects that are easily probed at high redshift. If I were to cut the dynamical mass of that system by, let's say, a factor of 100, I might have a source like this one. So this is an HST image of DDO 165, a source that's relatively near and dear to my heart. And you'll see a couple of very important differences from the previous disk-like galaxy. That grand design spiral structure has disappeared. It's replaced with an irregular flocculency in the stellar population. All the parameters are less and more extreme, and these dwarf irregulars span quite a prodigious range in absolute magnitude space. Depending on who you ask, they might say something more positive than -18 in the B band, but that range then covers many orders of magnitude in brightness. And if we go all the way down to the most faint objects that are known in the local volume, this is an HST image of Leo P, and here the stellar mass is down at the 10 to the 5 range. These sources are very, very small and underluminous, and therefore they're very difficult to detect. Now, these sources are critically important for our understanding of cosmology, and there's a lot of reasons why this is true. They're the most numerous type of galaxy of all epochs of the universe's evolution. They almost certainly played an important role in the cosmic reionization, standing alongside the AGN, being some of the first luminous objects to emerge from the cosmic dark. But they're also unique laboratories. They can inform upon astrophysical and cosmological questions that can only be informed upon by galaxies in this mass range. So let's think briefly together what some of those questions might be. First, addressing some of the tensions in the lambda CDM paradigm. For example, the missing satellites problem describes the mismatch between the predicted number density of low mass halos around massive galaxies and those that have been observed to date. And while baryonic physics is closing the gap between these two estimates, there still exists a discrepancy. And only by studying the lowest mass galaxies can we get new insight into what's happening with this tension. Likewise, the so-called too big to fail problem describes the over-prediction of numerical simulations, predicting overly rapid rotation or over-dense halos, much more dense and rapid than what are seen in the local volume. And so the predictions from the simulation suggest there should be more galaxies of this density and rotation velocity that we simply don't see. So finding galaxies in that mass range is critically important, and unpacking the physics that's at work there. These low mass galaxies can uniquely inform upon the UV luminosity function. So here's a plot from a recent paper showing some JWST data, extrapolating out to the highest redshifts, going beyond 10. And you'll see here a pronounced dearth of objects in the dwarf irregular luminosity range. Remember, before we noted that all of those irregular galaxies are off the right-hand side of this plot. So even with mighty JWST, this population remains beyond observational scrutiny at the present time. And so the only way to study the physics at hand in these systems is to go to the local volume. And then finally, fundamental scaling relationships like the baryonic Tully-Fisher relationship can, of course, only be populated in the extremal portions of parameter space by these low mass halos. And so each and every one carries value in terms of being able to populate fundamental scaling relationships like this one. So having convinced you, I hope, that these objects are cosmologically important, let us ask the question, do we know all of them, and can we study them holistically? And of course, finding them is very difficult. They're underluminous objects, and trying to accomplish a full census of these galaxies in local volume is a non-trivial task. So we might come about this in two different ways. The one that has gotten a lot of press recently is the blind H1 survey. So we could think of this as H1 first, optical second. And so here is Arecibo, may she rest in peace. I was loosely involved with alfalfa, and so it's a bit near and dear to my heart. The alpha receiver allowed the sky to drift over about 7,000 degrees of sky and gives a catalog of something on the order of 30,000 galaxies. And this was a Herculean achievement. Riccardo Giovanelli and Martha Hades led the effort here. Many, many decades of person power and dozens of PhD theses and manuscripts have come out of this work. And one of the crowning accomplishments is a population of objects that have low H1 masses that are in the local volume. The so-called faint end of the H1 mass function has been populated with some statistical certainty for the first time. But you'll notice as we go to the lowest mass bins that the error bars still remain significant. And that means that each and every contribution, each new galaxy that we find in this mass range carries intrinsic value in terms of improving our statistics. Of course, knowing where those galaxies are enables all manner of follow-up astrophysics it's very rich, but it's of course not the topic that I want to spend a lot of time on here, but just to wet your whistle, on the left is an image of Leo P, a very famous star-forming galaxy discovered by alfalfa. This is one of the most metal-poor galaxies known in the local volume, and early H1 contours from the VLA are shown at left, and a subsequent deeper VLA dataset on which one of the co-authors of Alexander's paper, Will St. John, a Macalester student, is leading the effort to push these data through their paces. Likewise, with a big sample from alfalfa, we can gather a sample of sources and bring observational scrutiny to bear on each of those. And so the SHIELD campaign is underway to do just that. But of course, this is not the nature of the talk that we're giving here. This is what's gone before us. And so the question is, what are we doing differently here in the Nazarova et al. Thesis? So specifically, this is a by-eye scrutiny of the DESI Legacy Survey imaging products. The by-eye scrutiny is brought to bear on approximately 50 relatively isolated gas-rich massive galaxies and their local surroundings, and then a fair coverage of the field looking for patchy flocculent overdensities that could be classified as candidate local volume galaxies. Here is a plot of the entire sky with approximately 5,000 local volume galaxies shown, color-coded by the Devacolure's morphology, early type galaxies in red, late type galaxies in blue. And if you have keen eyes, you'll see both a dotted and a solid blue line. And this indicates the footprint inside of which primarily Igor on our team has analyzed all of the square degrees of sky in the DESI products, looking for these patchy, irregular galaxies that haven't been yet cataloged. I want to stress how difficult this work is. So to demonstrate that, I'm going to show you two things. The first is a projection plot of the known galaxies surrounding the Sombrero galaxy. That is at field center, and its virial radius shown in the circle. Previously known galaxies in the surroundings are given by circles, either early type in red or late type in blue. And newly discovered objects in this campaign are starred with the same coloring morphology. So you'll see here we've introduced on the order of 12 new candidate objects in the surrounding area of the Sombrero galaxy alone. And this is hard work. I can't stress how impressed I am by the diligence and the care that Igor has brought to this. And I'll use an example here to demonstrate the discovery of this dwarf 0139 plus 1433 is really remarkable. It's roughly equidistant between mighty M74 and NGC 660, a famous merging galaxy. And identifying this object required the systematic searching of very, very busy sky over many, many, many tens of degrees. And just to give you a sense of what that effort looked like, this is going to be a sort of a rapid fire pan from each of those targets moving up to the position of the target that Igor discovered. And as these fields move by, you'll see many regions of flocculency and patchy emission, each and every one of which had to be examined by hand and attempt to be matched to existing optical catalogs in order to understand, is this a newly discovered candidate galaxy, or is this a source that we might have already known or had been cataloged in some other way? And so as we end the movie here, you'll see this is one of the discovered sources. And imagine all of the time and the effort that had to go into parsing all of those many tens of degrees of sky. So what's the reward? The reward is a sample, as of this writing, of approximately 150 candidate local volume galaxies. This is still a work in progress, but the contribution to the local volume census is significant. And while, of course, we would need HST to tell us is the source identically within, say, 10 or 12 megaparsecs or not by a TA or GB measurement, it nonetheless represents a sample that we should explore in great detail. And it compares very favorably, for example, with alfalfa. To give you a sense of what that sample looks like, I'll show you here 2 arc-minute by 2 arc-minute DESI cutouts on some of the candidate local volume galaxies. Each of these has a nondescript name, dwarf with a code based on the right ascension and declination. And as we pan through these, your eye does a good job of extracting the astrophysics. You see that these sources are irregular, patchy, in some cases with regions of higher optical surface brightness, which might suggest, being a ground-based observation and with its irregular morphology, these are star formation complexes or star formation knots in the galaxy. They all seem to share this blue color, and all of those aspects taken together suggests that these are promising candidates for detailed exploration with the GBT. So at this point, we know where the candidate objects are optically, but we have no information, or we have little information about their velocity. Enter the GBT. So the campaign that we then kicked off as part of Alexander's thesis was to begin to observe this sample of candidates with the GBT. So here's an all-sky projection plot. The galactic plane is shown in green, and the location of the 6 mentioned spirals from the abstract are shown for you here. And then the 105 targets that we've observed so far with the GBT are shown in black. The observational setup, I won't spend a lot of time here, but we have 2 programs running, and we shifted the 23 megahertz bandpass to give us instantaneous velocity coverage from about -500 to about 4,000 kilometers per second. It avoids the RFI out at 8,000, and it also gets us a little bit past the zero velocity Milky Way emission. And we invest approximately an hour's worth of telescope time per source. It's a position switching campaign, and we achieve a typical RMS noise of about 3.3 millijanskis in this effort. So I want to stress that the GBT is a wonderful instrument to use. We really love the hands-on nature of it. And so here's an image of myself and two of the McAllister students who are the sort of the trail end co-authors on the Nazarova paper, Lila Shizgal, who just graduated on the left, and Will St. John on the right. And we're looking quite pleased with ourselves having this nice high signal to noise ratio detection even in the raw scans from the GBT data. So now let's think about some results. So here I'm showing all 77 of the detected H1 profiles. Some have more modest signal to noise ratios than others. But to zeroth order, we could, of course, spend the rest of our talk talking about these profiles. But to zeroth order, we see the characteristic Gaussian-like distribution of H1 for most of the sources. There are some asymmetries in the line profiles. This indicates perhaps some interesting gas motions in the system. We see a couple of very intriguing double-peaked H1 profiles, which in this mass range is somewhat rare. An example is at the upper right in 1247-08, and I'll show you another in a moment. We also see a couple of sources that are very close to the Milky Way. They have low recessional velocities, and in some cases, we're fully contaminated, and we can't make any conclusions about the nature of the source. We could spend the rest of our time talking about this, but we don't have time. We want to talk about some other things. So statistically, it's a pretty good batting average. 77 of 105 of our observations are detected with confidence. And again, I want to stress that this represents a significant step forward in our understanding of the local census of dwarf irregular galaxies. Let's think a little bit more carefully now about the properties of those detections. So I'll show you the same plot as before, but now I'm going to color code the detections and non-detections in blue and red, respectively. You'll see no systematic areas in which our search was unsuccessful. Stated differently, none of our observing sessions were adversely affected, one more than another. And we have a nice distribution on the sky of these sources. If we then look at the comparison of the properties of our overlapping sources with the Fasci catalog, which was published more or less contemporaneously with our second observing program, we see almost identical average parameters in terms of the velocity, the line width, and the total flux integral, with modest dispersions about those mean values. Now let's think about the optical morphologies of these detected sources together. A few are obviously missing one or more filters, and hence their odd colors, but to zeroth order, all of them share the commonality of the irregular morphology, the blue stellar population, and in many cases, very obvious regions of higher surface brightness. Your eye does a good job of telling you that these are blue objects. We can quantify that, and then we can compare that to the average colors of the non-detected sources. And in fact, the detected sources are, as we might expect, bluer than the non-detections. Now, if you have keen eyes, you might say, some of these look a little bit confusing to me. Some of these I might have expected to detect in H1, and I didn't. For example, these 5 appear to have that same kind of flocculency and overbright blue regions. However, preliminary optical spectroscopy that's ongoing with the 6 meter over in Russia suggests that these are very low velocity sources in which the H1 line is almost certainly contaminated with Milky Way emissions. So we can't make any further conclusions on the nature of the H1 in those sources. So now we know where the sources are, and we've given a fair summary of the results in the Nazarova et al. Paper. And at this point, I'm gonna diverge a bit from following Alexander's paper and tell you about some new results from follow-up VLA observations, because now we can extract the physics on a spatially resolved basis for these targets. So in this pilot program, 25A170, we observed 6 of these sources. The data came in very recently between March and August of this year, so it's a bit hot off the press, if you will. These are the 6 sources that we observed. Note at the top center that one of them is one of those curious double peak profiles. And I'm going to show you the preliminary H1 data products for a couple of these sources. So let's dig in. First, VV507. This source, you can see very clearly, has some regions of ongoing star formation in the eastern portion of the disk. Its flocculent nature is very apparent, and the gorgeous GBT profile shown at right suggests that the VLA observation of this target will bear significant fruit. Next, I'll show you the H1 data cube. So just to get our bearings here, as a function of right ascension and declination, this is the projected H1 surface brightness. Each channel here is separated by approximately 4 kilometers per second and change, and the synthesized beam is at the lower left. So we have approximately 6 or 7 resolution elements across the source. It's nicely resolved, and again, this is the CND configuration data imaged simultaneously. We want to unpack those data, distill them down into 2 dimensions, and allow a one-to-one comparison with optical imaging. And so remembering that whenever we collapse the 3-dimensional data product to 2, we lose information. Let me show you what those moment maps look like now. Going forward, the presentation will be in the left column, the H1 mass surface density, here calibrated in units of 10 to the 20 atoms per square centimeter. In the central column, the intensity-weighted H1 velocity. The isovelocity contours span the range shown in the color bar. And on the right, the same contours of H1 mass surface density as shown in the left panel, overlain on the optical 3-color image from DESI. The synthesized beam is at the lower right, and when appropriate, information about the contours is shown in the subscript. So at deconfiguration resolution, we marginally resolve the source. No surprise, there's 2 to 3 synthesized beams across the target, and it's very nicely localized. If we go to the C configuration, we get, of course, longer baselines, lower surface brightness sensitivity, but a smaller synthesized beam, and we recover a much, much higher H1 mass surface density maximum. And intriguingly, that H1 mass surface density maximum is almost exactly co-spatial with the regions of ongoing star formation. If I put all those data together to give us maximal sensitivity, this is the C and D configuration data together. I see these very nice to 0th order straight isovelocity contours with a little bit of kinkiness to the right-hand side. But there's also this wonderful H1 mass surface density that's almost exactly co-spatial with the eastern side of the disk. And so this just wets our whistle on the type of astrophysics we can undertake with one of these data cubes. Let me now show you the second example, this curious double-peaked system 1459 plus 44. On the left is a zoomed-in image from DESI, the color image, and you can see these 2 very, very bright, apparently bright pockets of what appear to be ongoing star formation. Remember, these are broadband images, and an H-alpha image would be necessary. But all indications are this is an actively, aggressively star-forming galaxy. As before, the synthesized C and D configuration H1 data cube is shown here. The disk is beautifully resolved. The synthesized beam size is on the order of 17 seconds of arc here. And you can see a wonderful amount of substructure in the neutral hydrogen disk here. The gas is very nicely resolved, and it suggests that the source is possibly modelable. Let's do what we did before and break this down into the traditional moment map. So the low resolution, approximately 40 arc-second beam deconfiguration observation is shown here, contours of H1 mass surface density, isovelocity, and then the contours again of surface density on the optical on the right. A nice localization. As we go to the C configuration, we get a much, much smaller synthesized beam, and we see a very strong pocket of star formation, of high H1 mass surface density right smack dab in between those 2 regions of star formation. We put it all together for maximal surface brightness sensitivity here, and we see this lovely velocity profile that suggests that the source should, in principle, be amenable to detailed dynamical modeling. And so we dug into that. We used the 3D Barolo modeling package by De Teodoro and Fraternali to do this work. So what you see here are plots of the moment 0, moment 1, and moment 2, data, model, residual. And this allows an easy snapshot to evaluate the efficacy of our modeling. The moment 0 and moment 1 maps are described almost exactly. The residuals are trivially small. The dispersion, the magnitude of the dispersion is less than the magnitude of the rotation. And importantly, in this game, the uncertainty on the dispersion is much less than the magnitude of the dispersion itself. And these are the 2 telltale signposts of a modelable galaxy in this mass regime. Previous experience has shown us that the lowest mass galaxies are oftentimes dominated by dispersion and will have comparable magnitudes of velocity dispersion versus projected rotation. Not so in this galaxy. The position velocity slice looks just about as nice as we could ever hope to get in a galaxy of this mass range. Very nice solid body in the center and a modest flattening of the rotation curve. This is not yet inclination corrected, and we should study our parameters. So let's do that. Here, as a function of position in arc seconds, are various dynamical parameters, some of which are more important than others. At the top left is the unprojected rotation curve, and it's a robust curve because the magnitude of that curve is much larger than the dispersion. That's the top center panel. And the H1 mass surface density is a monotonically falling function, which means that we can model the asymmetric drift correction quite well. All of this is meant to say that our rotation velocity is fairly robust at approximately 50 kilometers per second and an angular separation of 70 seconds of arc. And remember now, this is a heavily resolved system with 4 independent data points across each side of the disk. Now, we don't have an exact distance. Let's use a placeholder of 10 megaparsecs. It doesn't really matter which value we choose for this ratio, but the dynamical mass far outstrips the summation of the baryonic masses in this source. And if you have keen eyes, you'll be able to convince yourself that that likely holds at all radii. Even if we were to go all the way down to the very first ring, we're at 30 kilometers per second rotation, and we still would have a larger dynamical mass than what we see for the baryonic components. So all this is meant to say, this dark matter-dominated, gas-rich galaxy was discovered in the DESI imaging products alone, and follow-up radio observations have revealed a wealth of astrophysics about the system. So let's think now about the next steps in Alexander's thesis. Of course, we're continuing to build the census. As I mentioned before, the optical search is work in progress. It's not yet completed. But as we build that census, we will continue to observe with the GBT. And it sounds like on September 26th, hopefully we'll be getting much more busy again. So the next program in the queue is 25B122. This is with Alexander as the PI, and we'll acquire approximately 30 some new H1 spectra to continue to wet our whistle. In terms of the concrete next steps, of course, we're going to begin that data acquisition shortly. We have some VLA data and also some GMRT imaging of selected systems in hand. I didn't show any of the GMRT data today. And then there's a supporting campaign with the 6 meter to acquire a deep optical surface photometry, including H-alpha, and also some emission line spectroscopy of the sources to understand their physical properties. And with fingers crossed, Alexander will be presenting those results possibly at a future GBT Science Community webinar. So let me leave you with our conclusions here. The GBT observations of these optically discovered candidate local volume galaxies has thus far paid very rich dividends. We have a collection of some dozens of individually, of heavily resolved sources that observational scrutiny can elucidate the astrophysics at hand in these systems in exquisite detail. And our VLA follow-up campaign is just in its early phases, but has already demonstrated very, very promising proof of concept. And then, of course, the further candidates, as Igor continues to dig into the data, will come forward and make for interesting projects in the future. I want to say thanks to the organizers for inviting me to present here today. It's been a great pleasure to see all of you and to talk about this interesting campaign. I want to give a special acknowledgement to Tony Minter. Thank you, Tony, for being a great project friend to us, especially in the early phases of the program. To the entire staff at Green Bank for keeping the observatory so healthy and such a lovely instrument to be using. And thanks to each of you for being here today. I'll stop there.
Thank you, John, for a very interesting and excellent talk. It was quite nice to see this data. Remind people to put in their questions in the Q&A, and we already have several questions that have come in. The first one is about the double peak object and they're asking, do you think the double peak object may imply rotations that are residing in the higher dark matter halos, confining the object?
That's an interesting question. All we can comment on from the VLA data right now is the angular extent of the H1 based on the highest surface brightness sensitivity observation that we have, and I showed those results. But it's an interesting question. We can dig into that further.
Okay. A question about searching the optical survey by eye is a lot of work, and the person asking the question is wondering if this could be done by AI and automated searches would be helpful.
That is an interesting question, and I'm afraid I don't have the skill set to answer that. Igor Karachentsev has done most of this work, and perhaps there's others behind the scenes as well. But Igor has done most of this work, so I think he would have to answer that question. But I suppose if it could be done, it would have been done. And there's the value of the human eye, I think, is always very important. There's a decision-making matrix that happens there that I think is very important. Okay.
A question, they're wondering about the method used for identifying the dwarfs in the sample. You mentioned manual scanning of DESI. Could you remind us why this method was used? And now that you have a reasonably, well, that's the first question. And now that you have a reasonably large sample of galaxies, could you possibly use, this is machine learning to identify additional candidates from DESI?
Yeah, I suppose we now have a prior on a machine learning approach, right? We have an answer, so we can ask the machine learning to go in and do that. I don't know the status of that work, unfortunately. Like I said, that's mostly been undertaken by Igor. And as other surveys come along, of course, with the advent of the new observatories that are on the near horizon, studies like this, I think, will only continue to become more important.
I just had a technical question, and I might have missed it. How much time did you have on the D configuration and C configuration to get that quality data to?
Yeah, that's a great question, and I didn't provide those details, so thanks for bringing that up. So the award was for 2 hours per source in the D configuration,
Mm-hmm.
and ostensibly 5 hours per source in the C
Okay, yeah,
configuration.
yeah, you had to go higher, deeper with the C.
Yeah,
Yeah.
but it was slated as a filler project, and unfortunately for both of the data sets that I showed you, we actually were only able to acquire one of the C configuration observations. So,
Okay,
but
so we could.
nonetheless, it demonstrates concept. Yeah.
Yep. Okay. Some more questions have come in. What is responsible for the double peak profile or the implications of the double peak profile?
Yeah, I think this is just in some ways it's luck, right? So the galaxy is intrinsically massive. It has a significant intrinsic rotation velocity, and part of that was projected into our line of sight. And the velocity resolution of the GBT was sufficient to be able to pick up that projected rotation as we see it on the sky.
And then a question, any hydrogen recombination lines detected in these objects? I'm assuming maybe he's there. The question is just asking in general, not within your data set.
Yeah, that's an interesting question. I know there have been RL studies of star-forming galaxies, local star-forming galaxies, but they require a different observational setup than the simple one that we used. I suppose we could look into that, but we would want to target, of course, the most strongly star-forming, most powerful galaxies in the sample to take that as a pilot experiment. Yeah, but we have not turned that stone.
Okay. People can put in more questions. I had a side questions looking at how great that DESI data looked and going back to the Arecibo data. This is not directly related to your talk. So have any of the nearby Arecibo sources, are there any of those that don't have any of the little blue fuzz around them or any fuzz that have been seen? There appear to be. I know when some of them were originally found, people were saying, without stars and stuff. But since the quality of the optical data sort of looks like it is approved for low surface brightness, do you know what the status is on that?
Yeah, so I've played a minor role. A lot of this work has been spearheaded by Professor Kathy Rohde at Indiana University. So she and her group have done extensive follow-up observations of the darkest galaxies, which is we have a nice H1 centroid from Arecibo or Fashi, whatever it might be. We go to existing catalogs, there's nothing there. We take new images, there still appears to be nothing there. Then we have to go really deep and try and figure out what's going on. And to my knowledge, all of those sources have reasonable explanations at this point. To my knowledge, we still don't have a shining example of there's a gas cloud out there.
Okay, so
That's not.
you just have to, if you go deep enough, you find something. Is it?
You find some things,
Okay.
and some of Kathy's papers will speak to that. Yeah.
Okay, well, thank you for that. A few more questions have come in. The double peak profile means that you've reached the flat part of the rotation curves as shown in the major axis cut.
Mhm.
I guess that's a statement. I'm sorry. I start and a question. Do any of the dwarfs have H alpha photometry presently, or are there any with optical spectra on any of them?
Yes. So that campaign is, as I understand, underway. I wish we could allow my colleagues on the program to speak about that because they've been spearheading that component. But my understanding is that with the SAO 6-meter telescope, there is deep optical broadband and targeted narrowband photometry underway. And at least for the most promising emission line candidates, some spectra are already in hand. So the 5 targets that I mentioned that were probably of such low velocity that we couldn't extract an uncontaminated H1 profile, those sources appear to have very low velocities from preliminary optical spectra. So yes, that work is underway.
Okay. A question, is the baryonic mass in these galaxies typically dominated by stars or gas?
Gas.
Gas, yeah. And it was about a factor of 10, basically, if I remember right, on at least the one year you had the delay.
For the source that I showed the model for, the dark to baryonic is about 10, and the gas to stars in that case was about 2.5, 2.5
Oh,
to
2.5, okay.
Yeah.
And then a question, any fast comparable observations?
Yes, so I did show some statistics on that. So of the 77 sources that we've detected, 29 are included in the Zhang et al. Fashi catalog, and we have very favorable comparisons of the average properties of our profiles with theirs.
Yeah.
We could take that another step further, but for the preparation of this talk, I didn't do that aside from a statistical approach.
I noticed all the line widths and the measurements are consistent. Almost looked like the calibration was exact too. Do you know if they took if there's a systematic calibration difference between FAST or the GBT, or is that, it seems
That's a good question.
it's almost too good. It almost looked too good.
Yeah, I'm afraid I don't know the answer to that.
Okay, no, that caught my eye anyway. That's a side thing. Sorry for the digression. My guess is somebody might have taken out a 5%, systematic and looked to scatter along about it. Or maybe we're just exactly calibrated the same way. So who knows? Okay. Any additional questions? It looks like we covered a lot of questions. Oh, well, another one that just came. Any outliers relative to the baryonic Tully-Fisher relations?
I can't answer that question quite yet because a lot of work has to go into placing a source robustly on that plot, right? But to get that, we need to know its distance securely. We need to know its rotation velocity securely. And then we need to have a very robust measurement of all the baryons, which is to say a very deep optical or infrared image. So placing individual points on that plot is difficult. You can't do it with a single dish spectrum. There's more information that's needed. So that's work that we hope we'll be able to do in the future, but as of right now, it's beyond our reach.
Cool. And well, okay, I'll let this be the last question. Will James Webb observe any of these candidates? Or are you guys strong?
Perhaps. I think given their perhaps given their proximity, some of them are in close proximity to major important galaxies. It's possible that by chance they will be observed in a group study or something similar to that. Could we undertake some sort of systematic study of the sources with Webb? We probably could.
Yeah.
But right now, I don't know of plans to do that with the sample, but it certainly could be very interesting to do that.
Okay, we're going to end it there with questions. I'd like to thank John again very much for an excellent talk. I appreciate it. And yeah, when your students is prepared and you have updates, let us know and we'll get her on the schedule basically in the future. So thank you very much, and thank to everybody who showed up today. We'll have another community Zoom in 2 weeks, and let me quickly see what it's about. It's the first Derek Smith's and the first detection of circular polarization at 4.7 gigahertz excited OH maser. So in 2 weeks from now, 9/24th, and by that time we should be pretty close to starting up observing, or we'll know the status of that. So thanks again, John, and thank you everybody, and have a great day. Goodbye.